Today, we have Nathalie Cabrol, who's going to be speaking about her work around extreme environment exploration, which I think is the nice way of saying some of the most amazing things that she's done. She's a pioneer, actually, in high-altitude diving, which is not like really tall diving boards. It means, like, so if you have a body of water that's actually at 10,000 feet, to dive in it is different than diving, say, in the ocean. And would that be correct? Sort of, kind of, a little bit. It's complicated. Yeah, so 20,000 meters?
20,000 feet.
20,000 feet, because meters would be a lot.
Yeah.
Yeah, I mean, American, but
oxygen tank there.
Yeah, you need an oxygen tank. But she's here to talk about her work for eventually exploring the lakes of Titan. So I'm going to give it to her. So
thank you very much.
Join me in welcoming Nathalie. So.
Good afternoon, and thank you very much for the opportunity talking here. Google, this is my first time, so I'm extremely impressed by all the structures and buildings, and I mean, you have a very, very cool place around here. So it's a great pleasure to be here and to be able to talk about the Planetary Lake Lander, which is one of the projects that we're working on at Ames with the Intelligent Robotics group. And the Planetary Lake Lander is really about developing and testing a technology that will be relevant for the future exploration of alien seas and lakes on Titan. But also, it's a mean for us, because we are doing astrobiology research, to investigate the impact of the melting of ice on our own planet. And you will see the relationship between the two. So basically, we are building a robot, a smart robot, at least we hope it will be smart, to understand changes in planetary lakes. The Planetary Lake Lander is funded by the NASA Astrobiology, Science and Technology for Exploring Planets. It's a 3-year project, and it's a collaboration with a water company in the Andes, and I will go back later on why we're in the Andes for this project. And the education and public outreach is, or maybe should I say was, supported by NASA. So we'll see what happens with that. And PLL is led by the SETI Institute. I'm the SETI Institute senior research scientist, but I'm also working at NASA Ames through a cooperative agreement. So SETI leads the astrobiology science and the project, and the intelligent robotic groups at Ames leads the technology development and research associated with PLL. And we have a number of partners in this project. Some of them are in the United States, and they are working on instruments and on the science supporting the project. The University of Tennessee, some people at Bayer, the Channel Islands, University in Southern California, but also partners from Spain, from Chile, and from Austria. And we have an incredible logistical support from people in Chile and the US as well. So, why Titan? Well, you probably heard a little bit about it. Titan is a moon of Saturn, and it's barely smaller than Mars, actually. It's a fairly big moon. Just for scale here, here's Tethys, just a more regular moon of Saturn. So it's really more of the size of a planet. And what made Titan so fascinating? It was already fascinating. We knew it from the past mission, but recently in 2007, the radar detected the presence of lakes on Titan. And so Titan is the only place in the solar system we know of that has surface bodies of fluid. It's not water, it's methane and ethane, but it has a methanological cycle, like the Earth has an hydrological cycle. And so it's a completely new branch of robotics and exploration and astrobiology exploration that we can start on with Titan. So the other thing that makes Titan so very exciting, it's because pretty much you can consider Titan being like a past Earth in the fridge. It's extremely cold, it's very far away, 2 billion kilometers away from the sun. But at the same time is the only other planetary bodies in the solar system that has an atmosphere mainly composed of nitrogen like the Earth. And the other component is methane and other molecules, including ethane and other things. So what we are looking at here is taking the Earth in the past, but also taking it in the fridge. And a number of things happen in this atmosphere that are extremely relevant for the astrobiological search of life in the solar system and elsewhere than Earth, but also understand how life may have originated, because we know of a large amount of organic molecules there. So what we don't know of is, did we go from organic molecule to life on Titan? And this is probably one of the best candidates to go test that idea. So, speaking of the atmosphere of Titan, now we have Cassini. Cassini has been orbiting around Saturn and visiting the moons of Titan. We had a flyby only last week, I think. Very regularly, Cassini is passing by and mapping and doing a number of things. So we've seen that Titan is very dynamic. Just like Saturn, because it's orbiting Saturn, Titan goes around the Sun in almost 30 years. So it's a very long year. Each days of Titan are about 2 weeks on Earth. And the seasons are about 7 years long. So tell me about having a crappy winter on Titan. That must be long. And so when the seasons are changing, then you see clouds forming, and what you see here on the screen is the polar vortex that's forming in the northern pole of Titan. Now, what we see from space is very limited, just because the atmosphere of Titan is so thick that we have to use radar to go through it, a little bit like Venus. But we went around this, and the landing component of the Cassini-Huygens mission, actually the Huygens probe, landed on Titan in January 14, 2005. And as he went down through the atmosphere, when the clouds cleared, this is what we saw. And I really love to put this slide on the wall all the time, because it really looks like Bay Area when we are coming back on airplane. You know, you're landing in Oakland or in San Francisco, it looks exactly like that. So it's a very familiar landscape when you look at it. And so this was a few thousand meters above the ground, and then this is what we saw when we were on the ground. And if you are looking on the upper right of your screen, you will see that as we were descending, we were seeing dendritic systems that look pretty much like rivers on Earth. So that was very striking. And once we landed on Titan, then we discovered what I immediately say, oh my God, we are on the beach. Because what you see is a very flat, piece of land, and you have very rounded pebbles. And so Titan is this place that if you look at, will look extremely familiar. You will have rivers, you will have mountains, and you will have seas. And what you see here is not a landscape on the Earth, but it's actually on Titan. And what you see is really an estuary of many rivers coming into a sea. But the thing is that it's really a case of it looks like, it sounds like, but it's nothing like the Earth. Because the rivers are made of methane. The rocks that you see all around are made of pure water ice that is so hard there because it's so cold that these pieces of ice are being transported in rivers and torrents over there, and they are being eroded exactly like any type of rock on Earth would be eroded. So it sounds like home, but you don't want to be wandering around without a spacesuit, and you definitely, are not going to drink that whatever is running in this stream. So, but a very, very interesting, fascinating world. So the thing that makes it even more similar than Earth than anything else is the fact that we have what we call a methane cycle, exactly like the hydrological cycle I was talking about early on. So what you have is that you have bodies of methane, lakes and seas, and then you will have evaporation, and you have condensation, and then methane precipitates, and you have methane rain on Titan. And so what happens then is that in the topography, in the topographic lows, then you will have accumulation of methane, and then you will have lakes forming, ponds forming, and you can see this in this image here, where clouds were captured in the Mesoramia region of Titan, and then just after the rain, then you could see the lakes forming right at the bottom right of your screen here. So, what is also very much like Earth is that lakes will be filling in, but they also will be evaporating. And what you see on the left is what's happening on Titan and an analog here on Earth. So it's pretty much looking like the right foot and the left foot, but on the other side, on the wrong side of. So it's very much something we can understand. What we don't understand, what we don't know of, is really how the methane chemistry really works for life. What kind of world is this for, potential for life and for habitability? Here's another picture after 6 years, which is pretty much a season, showing the changes in those lakes. All right. What makes it even better is that very recently, we had the confirmation that there are high suspicion that there is a subsurface ocean on Titan. So you've heard about the potential subsurface ocean on Europa. You've heard about the under pressure water on Enceladus and a number of icy bodies in the outer solar system. But on Titan, it's even more important, I'd say, because there is something really important that we didn't understand before, was in the methane cycle, methane is not very stable at the surface. And so people wanted to understand how long those lakes were going to last, how they were going to be replenished, what is the methane cycle. And if you have somewhere a sink of methane, if there is really an ocean in the subsurface of Titan, then you have a mechanism now to have this cycle that we were talking about. So,
ocean of methane or water?
Well, it's an interesting question because, in the subsurface, it's probably most likely methane, I'd say, but it will have to have some ethane components as well, because we see that in the surface bodies at the surface of Titan. It's a mixture. We don't see, water is not stable at the surface. Now, what happens at depth, I just cannot tell you right now, just like that. So, the evidence for the ocean on Titan is really tidal. There is a flexing of the equatorial bulge as Titan goes around Saturn. And this is this slide is really to illustrate what I was talking about, where now you could have some very interesting salted ocean underneath the surface crust at Titan, and then a way for methane to be replenished, to circulate, and go from cycle to cycle. And those cycles are over 10,000 to 50,000 years. So this was an important discovery in terms of astrobiology. A cycle of life. Now, we know that those lakes and seas maybe, and we don't have a very good clue about what is the potential for life in terms of the chemistry of the methane. But if there is a place where life could be protected from cosmic radiation and from other extreme of the environment on Titan, maybe a body of fluid, just like on Earth, could provide a shield. So we really need to maintain, if we want to have life in the longer term on Titan, we need to maintain them at the surface. And so we have this way where the methane and the molecules, the organic molecules that may be the bricks of life, are now falling from the atmosphere into the lakes and oceans, and they are being kept there. And then the oceans and seas are being replenished. So it's an interesting potential cycle that has a lifetime, as I mentioned before, of about 50,000 years. Now, there was a little, I'm not a biologist here, but a microbiologist one day was asked, what kind of life can we have on Titan? And it would be most likely strange because we don't know the chemistry of ethane and methane. Smelly because it's methane, and we know what methane can smell here. It's not pretty. And explosive, I don't know if it meant by that you probably shouldn't be smoking. In the first place, you shouldn't be smoking, but if you have a Titan friend, it might be a bad idea, or just because of the difference of pressure of the atmosphere. The atmosphere of Titan is 1.5 times that of Earth. And so if you are inviting that person in your spacecraft or kicking out of the spacecraft, there might be some problem. And so also what in a more serious way, there is little solubility that chemists know about liquid methane, which means that there will be a lot of energy spent, and there is not that much energy that is received by Titan. So what they think is that if there is life on Titan, you can have small things, but you probably won't have flying dinosaurs. Alrighty, so that was the background for why it's very interesting to go to Titan from an astrobiological standpoint. And so as soon as the lakes were discovered on Titan, somebody who's working with our team, who collaborates on the PLL project for the past year now, wrote a proposal which I think is the most inspired project that NASA had in a very, very long time. Her vision, it's Ellen Stoffen, her vision was to send a robotic platform on Titan at the surface of the lake, and then let the wind and the current take over and start for the first time exploring an alien sea. And so they were in a discovery program which is very limited, has very little money, and so they had limited bandwidth and limited communication, so very little data, in fact. And when I saw that proposal, I said, it's interesting that we have a good deal of experience now with Rover at the surface of Mars. We pretty much know how to do that. We're improving on this, but we know how to do that. But how do you go about exploring an alien sea? How do you robotically do that? And this was the start of a thought process that took us in a couple of years to write the PLL project. And basically, PLL is about that, about how do you explore alien seas and lakes. You have to explore in a dynamical environment. As we saw, there are precipitation, there is wind, and you can expect, just because you are in the lake and there are changes in temperature on Titan, day and night, etc., that you will, and season, you will have stratifications changes of the temperature in your lake, during the day or during the seasons. And so you will also have turbidity changes, because turbidity is the murkiness of the water, and you know that during the season this changes. On Earth it changes because glaciers, for instance, melt, and as they melt they release a lot of sediment in the water. And there are other reasons why you could have turbidity changes. It can be an avalanche, there can be an earthquake, there can be all sorts of reasons. But when you are on Titan and you have that much limited amount of data and communication, you will receive an image now and then, and you will receive some data now and then. How do you put into perspective what you are seeing? It's not like on Mars where you have regular communication and you can, have a better idea what's going on. Sometimes you can see things in your data that you have no way of putting into perspective. So we wanted to address those questions. And this was the focus of the Planetary Lake Lander science. So now, how do you sail on an alien lake? We want to explore the role of the weather on the lake. How does weather affect the lake in terms of surface temperature, relative humidity, storms, wind, and waves? Because this is all relevant to Titan. And then, how does changes in temperature affect the stratification of the lake, the mixing and the diurnal cycle between the day and night, and also what is the origin of those changes? These are questions we want to address there too. And also, what are the changes in the triggers in the change of turbidity in those lakes? And also, how do you detect organics in the lake? And what are their cycle? What kind of analogy do you have between Titan and the Earth? So our question were really, how can we help Ellen and the Titan Mars Explorer mission to really address the critical question, to get more science by being smart, and to put our data into context. So, now the technology side of it. We really want, because a robot on Titan will be isolated, we want to produce a robot that is smart and that has an understanding of its environment. Basically, PLL is a step towards robotic awareness. I told the engineering team that basically I wanted the robot to stop short of writing the science paper. I want this robot to be able to understand what is important for the science objectives, learn its environment as it goes during the mission, knows what is the norm and what is off norm, and trigger operation on its own without having to wait for human being in the loop necessarily if something happens and they are not in the loop. So it's going really a step forward. And that requires not only, well, the body, the robot itself, but it also requires that you develop a number of things, including off-board and on-board autonomy and the development of what we call adaptive science. So basically, a robot that is aware and that is capable of making decisions without having human in the loops. And one goal as well of PLL is to develop exploration strategy templates. We do that all the time with Mars. When you have a specific task that you do regularly, you just build a template, and instead of sending long commands, you just send, template number X. Alrighty. Now, the problem is that we didn't have a very nice body of methane around here on Earth to explore. So we had to work with a working analogy, and this is where the deglaciation thing comes about. So we want a lake environment that's capable of helping us characterize the physical analogy of the processes that are going on Titan, even if it's not methane. And we want to understand what kind of processes will be a challenge for our exploration. Also, we need it because this is a short project. It's only 3 years, and we are looking at deglaciation and climate change, etc. You cannot expect to have the final answer about the causes and the impact of climate change in 3 years, right? People have been on this for 40 years now. So we still want a site where you have a good deal of change in the environment and very rapidly, so that we know that the robot is capable of picking up those changes. And we also want a science question relevant to astrobiology, because this is what we do. So this is how we ended up in the Andes. And we are looking at the impact of the melting of ice on the habitability of lakes in the Andes. Global warming is melting the ice worldwide, and as we know, as deglaciation forms, deglaciation forms lakes very rapidly, but the different phases of deglaciation will do different things to lakes. And deglaciation also alters the temperature of lakes, their transparency, habitability, and life. And this is also the kind of thing we'll be looking for Titan. The reason we're near the coast in South America is because we have very high interannual fluctuation of climate and also evolution of glaciers, and pretty much it's unpredictable compared to other glaciers. We know that some of them, most of them, are receding very, very fast. A few of them are actually increasing in the higher latitude, and some of those, like in the Andes, well, they are going up and down because there is this interaction between global warming and El Nino, and they are close to the coast, so they are getting sometimes more precipitation, sometimes less, and it's evolving very, very quickly. And also the reason we wanted to be in the Andes, it's because this is probably one of the places in the world most affected by climate change, but it's a lot less documented than the poles and the Himalayas. All right, here is a little slide to show you the glacier we are at is the HRN Glacier, and it's the white line here. You can see its evolution. It's nothing really very straight. The trend is down like everybody else, but it's going up and down and up and down. And as I said, there is this conflict between El Nino and global warming. So for us, the high variability of the environment was really the key to put a robot up there. Here's the lake in question. The lake that we're exploring is Laguna Negra. It's located 70 kilometers south of Santiago. It's not in the high Andes, but it's in the central Andes. At around 2,700 meters high, which would be around 9,000 feet elevation. It's a fantastic site, as you can see. It's a very large lake. It's 6 kilometers by a little less than 2 kilometers wide. And it was advertised for 12 meters deep. When I first saw a few publications, we ended up with a body of water which is 300 meters deep at our latest bathymetric map. And so that's a lot of water column to work with, and we're really happy about that. And it throws at us all kind of weather, but this is the joy of working in the mountain. Here is to illustrate the receding of the glacier. You can see the glacial scouring on the rocks in the here on the lower right in the image. This is when the glacier was there. You can imagine the HRN Glacier actually ended up in Laguna Negra, and then, year after year receding. The glaciation didn't start yesterday on this glacier. It started like everything else in this area 20,000 years ago, but it's accelerating very, very fast right now. The main supply from HRN to Laguna Negra comes through that little stream here, and this very nice aqua lake, which is about 100 and so meter wide, and that we call Station Lake. And there is a very important reason for that. It's because we have a station over there. It didn't have a name before, so now it's Station Lake. But this is really where the water is coming into Laguna Negra. And this is into perspective. You will recognize the Google 3D vision of the area on the right. No, on the left, that's the other right. I was stunned, actually, because on the left, this is the Google 3D of Station Lake and the water coming in. As you can see, this is a hanging valley now. And so you have a cascade that links, really, the stream to the lake. And you can see a photograph here of Victoria's Cascade. This one has a name, and this is where we want to be, because this is where the stream from the glacier is entering, and this is where we are going to see the changes in the turbidity of the water. All right, a little bit of touristic images here. These are the working tent. They look very small, but wait until you see what we do there. So these are really big domes, in fact. The one on the top left is a place where we have lunch and dinner, but it's also the working room, and we can fit 30 people without too much problem in there. And on the upper right and lower left, we have what we call the Robodome, where we have the engineering stations and people working there who are testing PLL. And on the lower right, we have the biodome, where the microbiologists are doing their work over there. So looking at the samples, etc. So when we are there, it's a little city, because we have 4 of those domes, and then we have about 20 small tents for everybody. It's a big thing to get there. About 1.5 tons of equipment and 20 people last year. So now. Time versus PLL. Time is the Time Mare Explorer mission of Ellen Stofan. And PLL, I just wanted to show you once again the comparison of the science goal. So Time mission on Titan would go there to understand the carbon cycle through the study of the sea and explore the limit of life. And our goal is to understand the impact of deglaciation on hydrological and carbon cycle of on this lake, and also lake habitat and biodiversity. What is the impact of deglaciation on life there? And then you look at all the science objectives that are listed there, and also some of technology objectives, and you just basically have to change methane for water and sea for lake, and we're doing pretty much the same thing as the Time mission. So it's an eye chart. I'm not going to read through that, and we talked already about that. Now, the hardware. So the Time Lake Lander mission is represented here on the upper left, and it's a 26 kilogram spacecraft that has a number of instruments on board, and the number corresponds to the names that I listed down there. Our puppy here on the right is about 1 ton or so, everything put together. Liam?
About that.
about that. So it's not exactly the same scale, but this is really the field horse that we're going to use to do things. And there are some differences, but there are a lot of common things. The numbers you see on the PLL side are similar in nature than the number of the instruments that you do see on the Methane Lake Lander. We don't have a mass spectrometer on board. We have it in the lab, which means that we need to bring the samples back. The same thing for the Raman spectrometer, which is looking at organics. And the thing that we do have that the Methane Lake Lander doesn't have is that we have a profiler, which is basically a multi-sensor parameter sound that goes up and down along a winch in the water and does profile, whereas the Methane Lake Lander will use the propulsion of the wind and currents to do profiles at different depths depending on the depth of the lake. So they're pretty much passive in the lake, whereas right now we are more in one place. This year we'll try to actually release the Lake Lander and do profiling as we go. But the Lake Lander cannot do that. Otherwise, we have pretty much an equivalent payload than the Methane Lake Lander. We do also, because we have some goals that we want to achieve for the study of the climate change on Earth, we have a number of other things that we do have. First, we have a shore station that has, you see this on the upper left. The shore station gives us some information that are redundant when it comes to meteorological information. We do have a met station on board the Lake Lander, but this one is on the shore. We do have a redundant multi-parameter sound, but this one is fixed on the buoy, not too far away from the Lake Lander. It's only at one depth. It doesn't go up and down in the water column, but it actually records data at a much higher resolution. And we also have another med station, and you'll understand why later. We have so many of those in the valley, in the Glacial Valley. In this image here in the middle, at Lake Station, we do have a stream gauge that tells us everything about the discharge of the water, the changes of the water in that stream, the temperature of the water. And this is the instrument that you see here. We have Gigapan, which is an absolutely fantastic camera that gives us huge panorama, really the kind of thing that would be really difficult to get on a time mission to Titan, because you have 7 gigabytes of data to download. So pretty much your mission is right there, one image. But we use it in many different ways to survey the environment and to also do some check on the health and status of the robot. It takes picture of itself. And we do have an underwater camera that's named the Muck. And this one is there to survey what's happening in the water column right next to PLL. I'll talk more about that in a moment. We do have a few other things. We are doing some limnology and ecology, looking at what's in the water, algae, zooplankton, etc. And when really we are bored and don't know what else to do, we change a water sampler bottle into little submersible that we fit with a GoPro camera and a few hobo data loggers, and we throw that at 200-meter depth and try to record something. The GoPro didn't like it. But we got data. I'll show you some. We also use boats to do the bathymetry of the lake. This was something really important because bathymetry is also something that the time mission will do. So we recorded that data to be able to do some operation readiness test and have a database we can choose from. Now comes a data delivery system for the project. Here is a little chart that I prepared. So on the upper left, you see a satellite that's used. This is the Earth orbiting system. We are monitoring the evolution of the environment from the NASA satellite that are surveying the world, and this is Aqua and Terra, and we're using Aster as well. So this goes directly, it's on the computer. You can have access to that. It's public. You can work with that. And we are also using satellites for communication, obviously, with the robot. And there we have our Lake Lander. The Lake Lander has different ways of communicating. We can communicate with, through the shore station, and the shore station can communicate to the Lake Lander. and communicating with the satellite and get comm to the user at NASA Ames through satellite comms. So we have this little relay going around here. We can talk or phone to the robot. We get data daily and health status daily. And then the data, the science data and the health status data of the probe is archived on the XGDS. And the XGDS is developed by IRG as well. And it's what's called the Exploration Ground Data System. And it's really a place where all the data comes in, but it's not only a place where the data is passively stored. It's a place where you can see it live as the lake is changing. So you have this vision of the lake changing, but there is also a place that the analysis notebook where you can get this data and start working with the data within the site itself. So it's really a tool where everybody can share the data. All the scientists can get, the microbiologists, the ecologists, the earth scientists can put their data there, and people can work with them within that environment. And there is also something that I'm sure Trey will love to talk more about later on, which is this Google map vision of our own data. We developed this bathymetric map of Laguna Negra, and Trey already built that. It's wrapped on a Google Earth map. And this is extremely useful because it allows us now to not only have those maps, but when we do samples, have those samples co-register. We can go there and really use them as a working tool. Okay, so now the technology milestone for the project. The idea was to develop this robot, and in 2011, which was our first year, it was really hands-on, trying to understand what kind of platform we were going to use, and pretty much receiving it and pulling it apart and trying to understand how it worked, what kind of power, etc., etc. And we took Lake Lander for the first time in the field in 2011, and that was pretty much debugging time for 3 weeks, 4 weeks. And then we left it in the field. We have all sorts of communication problems, and we swore at that point that in 2012 we would be smarter than that. But we already had a little bit of data that was very encouraging. This year, the engineering team completely redesigned, and including some recoding of the probe, and they did an incredible job. And PLL V2 was really much improved. It was deployed in Laguna Negra in December in 2012, and was put in a permanent mooring position for all this year, so that we can collect data and see what kind of information we have, and what is the quality of the information that we have. And then we had a little bit of science and technology operation from the field. Ellen Stoffen came, and we showed her how PLL was working. And we had her coming to some realization on a few facts, and I'll show some of them later on. And this year, XGS came online. So this is live, and the science team can use it. It is accessible only by the science team for the science data, but we do also have a website, Planetary Lake Lander, on the SETI Institute website. Already a few more photos to summarize what happened. On the upper left, you see pretty much, pieces of equipment in the backyard at NASA Ames. And this thing coming together day after day. And on the upper right, that was what we call the splashdown, with the pontoon being released in the water. And then on the lower images are really what happened to make it happen, which is calibration of the multi-parameter sound, really putting together all the pieces. And then on the lower right, you see Liam spending a good deal of time in the temporary mooring position, just going back and forth with the boat and making sure this thing was working. And it did. December 12th was the day that I think it went online and working for the first time. So that was the day that Lake Lander was being moved from the temporary mooring position. On the left here, you will see how much that chair that I loved really is a very good analog for planetary exploration. On the upper right and lower right, you see the Lake Lander being moored in its final position right here, and right here is the position of the redundant sound. This is what it looks like right now, except that there is a lot of snow on top of it. But you see the instruments I talked about with the communication. The engineering team added a wind turbine just because of the winter and because we are in a very steep valley, which means that we don't have much sun during winter over there. And so we needed some added on power, and the wind turbine did that. And you see the distribution of the instruments and communication system right there. The MACCAM, I talked to you a little bit about that. We really do want to understand what's going on in the water column. And this is something that you can imagine can be used to actually look for microbial life in a water column, but it can also be used for ecological purposes if you are looking at how turbid water is, how murky, and what kind of things are passing through the water column at different time of the day. So Carnegie Mellon is developing this, but it's just not a passive camera. It's also a camera that is going to do adaptive science. And it's actually going to track whatever passes in front. And in this case scenario here, we ask it to track copepod, and copepod is this zooplankton that you see the little red critter on the upper part of the slide. So this is pretty much what happens when they develop their tracking system. So this has been developed and tested this year off-board, and in the coming years the camera will be now connected to PLL and will be watching what's going on and will give us some report about what's going on in the water column. I think this is a really interesting aspect of adaptive science where you can get a lot more information because now your camera is taking the picture, it's segmenting that picture, trying to understand what's going on in there, and basically sends you only the information that is really important. So you are not only having the information, but you are saving a lot of bandwidth. Now, for the last part of the talk, I'm going to give some results about the science and also what is our vision for 2013 for PLL. In terms of the deglaciation here on Earth and the causes of changes in the lake, what we've seen is that when you look at the data, you look at average, it would seem like nothing is happening on the glacier at HRN. And the temperature doesn't seem to change on average, etc. But if you are starting to slice that time into season, you will see that something really interesting is happening. Summer temperature hasn't changed that much. Spring hasn't changed that much either. Winter are getting cooler. But what is changing really is the fall in this area. And this is the critical point, because fall is really the season where snow is falling. So two things are happening. If the temperature is too warm for snow, then snow is not falling, water is falling and goes directly into the lake or into the water reservoir. Or if the snow is falling, it's falling on the ground that's warmer than it should be. So once again, you have more that goes directly into the runoff and doesn't go back into making ice for the lake. So what you see here on the extreme right of the slide is to show you the balance between snowfall and snow melt, and this definitely shows an increase. There is a lot more melt happening right now. So we are looking at this impact, and also we are trying to learn to support a mission like time. It would be really hard from space because of the thick atmosphere. But here we are doing it because, once again, looking at the climate change here on Earth, we understand that looking at satellite imagery and looking at the mineralogy and looking at the thermal response of the ground, then you can understand the changes that are going on. The thermal imagery is going to give you some idea of the size of the grain that is in your watershed. So the response, the temperature response of the ground also depends on the size of your sediment. And we see this changing year after year, and then you have an idea of what kind of sediment and the size of the sediment is going into the lake. This is in the watershed. And so this is going to impact your life and your habitability in the lake as well. So If we were going to do that on Titan, we would need to have an airplane. We couldn't do that from orbit just because we cannot see through it. But this is definitely using thermal imagery is definitely something that is a tool as well to understand the causes of changes in the turbidity of a lake and the nature of the sediments that going into it. In terms of the lake itself and how you go about sailing a planetary lake lander on an alien sea, one very important parameter is the wind, of course, all right? So there are winds on Titan, and we know that winds can form waves when they pass 1 meter per second. And so what we did here was to study the wind at Laguna Negra and try to see what kind of effect they had on the lake. So obviously, one of the first effects are the waves. And this lake, which is, I'd say, only 6 kilometers, it's not a sea, but it's very deep, 300 meter deep, can generate waves that are about 1.5 feet in no time. In no time. We saw that coming at us within minutes, I'd say. And the weather can change very rapidly. So we don't know what will happen on Titan, because at the time where the mission would be supposed to land, if it had been selected, the wind would start to pick up because of the seasonal change. So they would have wave, but we're not expecting wave that would be 1.5 feet high. Still, wind is definitely something you need to take into account. Then you need also to understand what is the lake effect. If you want to understand Titan, what is the lake effect on temperature and relative humidity? So we have been studying this too, and you see this in the different color line that are here on this graph. Now, Trey put this slide together today because this is data we received today, Trey, right?
Found it yesterday.
Found it yesterday, okay. So one thing that the Titan team is aware of is obviously the role of the tide because of Titan. There will be current related to the tides on Titan. But what they didn't think about was that the lakes have oscillation on their own. And the sea is the same thing. You can generate this oscillation. It's just like imagining the breathing of someone. Okay, you have wind on the lake, and then you have a wave that's carried into that lake. And this well will go down as time goes by, but there is a rhythm to that, and there is a cycle, and we call these sessions. And you can theoretically, just with a piece of paper, knowing the depth of your lake and knowing its dimension, figure out actually the oscillation, the wavelengths of those sessions. And we did this little exercise with Trey because we thought we were seeing some, and we changed the data resolution on our water level sensor, and this is what we picked up. So there are sessions, and the period is about 30 minutes. We would have to know much better the depth of the sea of the lake where a Titan robot needs to go if we wanted to understand what is the oscillation, the wavelengths of a sesh. But they will have also to figure out a way to work with those because it depends on the wind, depends on the number of things. But definitely this will take their robot from one place to the next. Bathymetry. This is one point where definitely Helen came to some very, very hard realization. So the idea is that as the time robot lands or splash down on the lake, it will use the wind. There is no propulsion. There is also no way of stopping it. It's just a passive robot going on the lake. And every hour or so, it sends a ping with a sonar to do the bathymetry of the lake. So 8 o'clock in the morning, we take Helen on our boat. We have a bathymetric system on, and we sit in the middle of the lake and say, okay, let's beat a probe and see what happens. 1 hour later, we were about the same place because there was no wind. So I said to Hélène, two things are going to happen here. If you don't have any wind, you will have a very, very high resolution map of your lake from a very, very small area. But if you have lots of wind, you are going to have a very low resolution map of your lake. So these are the kind of things that all of a sudden operationally you start to understand. If you have a passive robot, it's not going to be a simple thing. And also if you are passive and if there is an obstacle, you're doomed. So these were the kind of rationale and reasoning we went through with her over there. all of a sudden this mission took a different life, and for us too, because we didn't know what exploring alien season lake was going to be. So, in terms of the lake itself and what's going on here, I'm not expecting this to happen on Titan, but just because it's so incredible. As the glaciation progresses, lakes are becoming more transparent, at least at one phase of them. And this is a disaster for life in there, because for the first phase, when the lake is turbid, you have plenty of microbes in there. There is a large biodiversity, everything and anyone is there. But when the transparency changes and increases, all of a sudden UV goes through the water column. And whoever is not resistant to it gets fried. So those lakes still have lots of population when you're looking at numbers, but the biodiversity is going down, and you now have microorganisms that are resistant to UV. What you see here to the left is the water column of Laguna Negra, and this is taken at a time where the lake is at the murkiest. So this is spring, summer, and we still had light at 50 meters down, which means that this is probably, if we were going to have the same data in winter, it's going to be even more transparent because all of the turbidity and the sediment has settled down. So you see the curves right there. That probably puts this lake as one of the highest, most transparent lakes in the world. And you can still see the curve changes in light at the bottom of the lake, and this is 45 meters down. So, what life does, it follows the food. And so we hope that on Titan it will be doing the same thing. What you see on the left here are two charts showing the changes in chlorophyll and blue and green algae in the water column. One is really somewhere in the middle of the lake at the temporary mooring station. And at the permanent station here, where the Cascade is and where the nutrients are being brought into the lake, this is where you get most of the chlorophyll and the blue and green algae. Now, adaptive science. What you see here, and that will be the conclusive part of the talk, is some of the profile that we are getting from the Planetary Lake Lander. And typically, this is the kind of thing we would love to have on Titan. And what the robot is going to do is to be able to learn the changes that you are seeing in the water column. Here you have temperature, you have transparency, you have dissolved oxygen, and you have chlorophyll. And so what it does, it's picking up the changes in this environment. And what we wanted to do is really to try to understand what's going on, what is the cause of the change. And this is the adaptive system that we are trying to develop here. So what I put here in that box is a change in turbidity that's related to a change in temperature. And now we are going back to what I was saying at the very beginning of the talk, is that why is it important for us to be able to pick up changes in temperature and turbidity? Because these are the kind of changes we're going to pick up on Titan as well. And we want to understand what they are. So basically, when you have changes in turbidity in a lake because it's seasonal, you will have a very slow gradient of turbidity going up. If this is something that's related to a stochastic event such as an avalanche, your signal is going to have a very different gradient and go down in a very different way. And you can have also algal blooms and things like that, increasing your turbidity. So what we want to do this year really is to teach PLL how to recognize those. And once we have the algorithm ready for that, then we will try this inside over there. And hopefully we can make some demonstration. This is really the goal that we have this year. So 2013 will be really our testing time for PLL. We will have a robot, hopefully, that we can release in the lake. We will be able to drift like it would do on Titan, and also be able to pick up changes in the environment and tell us what kind of changes these are. So I'm going to go through this very quickly, but basically this is what the robot has to learn. It has to learn how to recognize changes in temperature, in turbidity, in water discharges, and in water temperature, and changes in chlorophyll and blue-green algae. Put that together and then come up with the right solution in telling us what it was. And finally, this is our timeline for this year. The field campaign, the net field campaign, will be in December, and we will have warranties this summer, beginning of fall, and working with the time mission as well to give them some data to think more about real mission to Titan. So thank you very much. I ran a little over. I'm sorry about that, but this is what PLL is about. There is still a lot for us to learn. But definitely exploring lakes and alien seas is a very, very different beast. I'm coming from the rover standpoint and exploring Mars. And it's completely different. It's completely different because you don't have as much command over your robots. It's not that you can drive it at this point in time if we are going with the concept of time. But maybe the lesson that we have is there are some flaws in that mission concept that we want to change, because going to another planet is hard. When you're succeeding in landing there, I think you should be able to steer a little bit your robot if you feel that there is a danger somewhere coming at you. So anyways, thank you very much for your attention. And just as the last slide, here's the crew of the pirate ship.
So we're all pretty interested in bandwidth, and we think in huge bandwidth numbers here. And you talked about having really low bandwidth allotments and presumably low computational allotments as well. Can you talk about why that's a hard constraint, that you can't just be like, actually, you know what? It's worth it to get more bandwidth back, so let's spend a little more money on better rockets. And
well, it's not only the rocket, and there are a number of things. I want to be very candid with you on this. I will not talk about the time specs, because this is proprietary material from Ellen, and I swear to her that I wouldn't talk about that. But I can give you an idea of why the limitations are what they are. This mission was proposed in the context of the Discovery program. And then you have that much money that you're allotted. And this is why they don't have an orbiter supporting them. And this is why they had to go now because of a direct to Earth that they can use. They are in line of sight. The season is going to change very, very fast now on Titan, and so it's going to be a lot more complicated even to communicate. But you have the constraints that are related to a program. But now if you want to say, okay, let's assume that the program is not the constraints, how would I do that? Well, sure, you wouldn't like to limit yourself. Once you're on Titan and you land there, you want as much information as you can, and you don't want to have one image per day, per Titan day. And so on and so forth. So how you do that? Well, you can put small orbiters or communication satellites, swarms. We do little things now that are not so expensive anymore. But it's not going to be within the Discovery program frame. Although the Discovery program is going to be recompeted soon now, so we'll see if Helen goes. If she doesn't, then maybe there's room for other options, and who knows? I mean, the private sector seems to be very keen on getting involved into planetary mission, and when you look at the cost of that, I think it's very feasible.
I'm just wondering, have you worked with, was there any idea to have kind of a rover right by the edge of the lake that could also go in?
Definitely not in the Discovery program. But what we did, that is not in the time mission, the shore station that we do have is already a relay showing us the perspective of what's over there on our shore, not on Titan, all right? But it's looking also at the Lake Lander. The Lake Lander is looking at it. So we have ways of seeing what's going on the shore, seeing the changes. Now you are talking about an integrated mission that will have a rover and a Lake Lander. And I'd say if you go that route, why don't you put an airplane on Titan or a balloon? And I'm just half kidding, because this is exactly the place where you want to do that. And I was talking about the thermal imagery that we're using to survey the watershed and the mineralogy changes. But then you can think about having those instruments on board 2 little airplanes or 1 airplane and following the Lake Lander, and just looking maybe what's ahead, because you don't have this vision from the Lake Lander. Maybe you can have it as a scout for your Lake Lander You know, you will more or less know where you are going because of the direction of the wind, and so maybe an airplane can go there and send you data and allow you to do some planning, a little bit like what we do on Mars when we are using the orbiter to plan traverses, or we are using panoramic images. But when you're on the water, there is more water or methane in front of you, so it's hard. But no, it's very interesting. You know, I'm completely sold to the idea of multi-robotic approaches, even on one mission. Swarms of robots are really good ideas, but they can become very expensive and very complex very, very quickly.
Yeah, I was wondering how much do you know about how the oceans behave there, or these lakes, like how strong are the currents, and also the differences between floating in water and floating in methane, because I guess the density is different.
Yeah, the density of methane is about half that of the water, so you're going to float. But for the waves right now, the seasons they were supposed to land on, winds were supposed to get up to 1 meter to 1.5 meter. This is what's modeled. And once again, you know, once you land, you know where your model went wrong. But this is what it is modeled. And so this is going to generate small waves. We're not expecting anything like a tsunami but now anything can happen. I mean, large waves are happening in lakes not only because of wind, but they're also happening because rocks fall into the water. You can generate very large waves because of that. On Titan, there is less risk to have asteroids and comets, you know, falling and generating a big wave, but that can happen. That can happen. We saw that the frequency on Mars is quite abundant. Did you see the paper a couple of days ago coming out? So new impact craters on Mars. This is not going to happen on Titan. The atmosphere is thicker than it is on Earth. But, you know, things happen. Things happen. So you can have large waves. So winds 1 to 1.5 meter expected. Waves at, say, about 10, 20 centimeter max. So it should be a smooth ride to some extent. And the currents are being generated by the wind, also by the sashes I talked about, but also by Saturn's tide daily. And I don't remember the number for the tides. I don't know if you have any idea, Liam. I don't remember, but they are a few meters per second.
How do you determine that what you see is life?
Great question. Well, if you have a rabbit jumping in front of the, that's always the response. We're not expecting a rabbit on Titan. But you know, as I said, once you land, this is when you know where you went wrong. But more seriously, I think that in the incarnation of Ellen's vision of exploration of Titan, time is a first step. It's not a life detection mission, but definitely they are looking at organics. So they are looking with Raman at organic molecule that they can find, and their abundance in the water and the changes of this abundance during the day, during season. Well, they won't last that long. But in the course of the day and night, the same thing as you would do on the Earth and that we're surveying. So they will be measuring that. Once again, it will be very, very limited. And this is always, unfortunately, the same theme that comes back with the time mission, not because it's a bad mission, but because it's very limited when it comes to what they can do. But the power of it is that it's the first time. This is the first data we're going to get, and with that data, we are going to prepare something else. Remember the old Viking mission? Viking mission on Mars had a life experiment on board. And we went with a live experiment on Mars, and then we landed there for the first time, and we had no clue what the environment was. And then when it came time to really interpret that data, it was really hard. Today, we still say, the results were ambiguous. But now we know that there are a number of things that can create the result that we saw that are not live. So the idea is you just cannot go to a place that is so completely different than our place. And Mars was so close compared to that. So methane chemistry, I have no clue. So the only way I think we will know that something is alive in front of a camera if it's jumping out of the water or moving in certain direction that mean that they are, not only driven by currents and by other things, but right now, time is not a life-seeking mission. It's a break of life, a little bit like Curiosity. Curiosity is looking right now, it's not a mission that searches for life on Mars. It's a mission that's here to say, where are the bricks of life present on Mars? So a mission like Time would do that, and I think this is a very wise first step.
So it kind of blew my mind when you started by saying, yeah, let's try just letting it drift. Right at the beginning. Like I'm thinking, well, I put a rowboat on a lake, and not very long I've got a broken rowboat, and I didn't go where
This is exactly what he's saying. But I'm here to make his life miserable.
So, yeah, can you talk about sort of the practicality of that and why it's a less bad idea than it sounds to my naive mind?
Oh, it's a worse idea than whatever you
why
have
it's a
in
worse
mind.
idea than even I can
But I'm
imagine.
conscious about that. I don't ignore it. And I'm not completely stupid either. So here's the idea. We definitely have to demonstrate that we can do the kind of science that we have developed. Because developing adaptive science on a platform that's not moving, that's anchored, then you have sort of a stable environment. The lake is what it is around your robot, and then you pick up stuff and it changes, and it changes because you are in one place. But now what we're saying is that we are going to send robots, floating robots on Titan. The thing is going to drift because this is what they had in their scenario. It is going to drift. So now we need to demonstrate that we can do that kind of adaptive science and pick up real changes as we go, which means that not only we have, a floating robot, but then we have to understand that the changes that we are seeing are not only related to the different places where we go, but also to something fundamentally important for the mission. This is very, very complex because as you move across the lake, you are changing environment and condition might change and you might trigger your adaptive system all the time. We have no clue about that. Once again, we are going to be hands-on there. And this is scary. This is scary from the adaptive standpoint, but this is also scary from the robotic standpoint. And the good thing is here on Earth we can do something. And the thing we're going to do is to put a couple of engines on board the platform, and probably someone on the platform as well. And so, which means that we will do this when conditions are okay, and so there is a lot of wind on that lake, but we know the time during the day where there is less wind, so we will do operations at that moment. I don't even want to think about starting to talk about night operation to the safety review board at Ames, but ultimately we'll have to go there at some point. And so if there was a realization to me, the first day we put PLL in the water was that going to Titan pretty much dead in the water is a bad idea. And so if there is something that needs to be changed in my mind is that this robot should have some mode of propulsion, if only an emergency one. A one that you don't want to use, all the time. But
that's a really scary looking rock. Maybe we should use up some battery power. That kind of situation, right?
Yeah, and for that you also need more bandwidth because you need to be able to see that rock, long before it hurts you. And in the kind of bandwidth and capabilities they have, I'm not sure we can do that really. And that goes back to the airplane or whatnot, a surveyor on top of you. Which could help you this way. So I really love the Time mission because it is the first vision of an exploration of an alien sea. By many means, it is a poetic, more than scientific vision of exploring seas, just like we did in the past, where you were putting a boat with people, on the sea, and let's go see what's in front of us, and we'll see. But in the meantime, it takes a long time to get to Titan. It is scary to be going through that atmosphere and splashdown. And it is, you know, you want the most out of it. You really want the most out of it. So if Ellen is going to resubmit, I think I would have a few suggestions for her. And if I was going to submit a mission, it would definitely have some different flavor about it. Thank you.